Hey guys, welcome to class number 8. We're going to continue on the theme of energy. In the last class we talked about Earth's energy budget, how it's driven by solar radiation, and how that energy comes in, gets absorbed, and then gets kind of spread through all these different heat reservoirs in Earth, and how Earth ultimately has this equilibrium or balance between energy in and energy out. So now we're going to shift a little bit and start basically talking about solar energy, and then next class we'll talk about wind energy. So the first part of talking about solar energy is to look at the idea of solar insolation. That is the pattern of solar energy, how that pattern is spread across the surface of the Earth. And this is important for one reason, because the distribution of solar energy on Earth isn't the same everywhere. It's not uniform. Instead, it's quite uneven, which means different parts of Earth heat up at different rates in different seasons, and we have to redistribute that energy through Earth by things like wind and ocean currents. So it's important to understand this to think about how wind and ocean currents arise. But also, on a practical level, solar energy is a great carbon-free source of energy, but it's not the same everywhere. It depends where you live, how efficient solar energy would be for your area. So we're going to learn a little bit about that today. So to build on that last motivation, here's the electrical generation in New England in 2012. You can see it's mostly fossil fuels. We got gas, oil, a little bit of nuclear. And if we look at other renewables here, it's only 3%. So that includes solar in that small 3% slice. But of course, solar is growing fast, and it's been a fairly controversial topic in Vermont. So it's good to kind of understand what the strengths and limitations of solar development are. So in this video, we'll do two things pretty quickly. We'll understand why higher latitudes get less average annual insolation, so they get less overall energy, and also why higher latitudes have larger seasonal differences in insolation compared to low latitude equatorial regions, which have very little difference. So before I get started, I want to show you this slide, and I'll show you this a bunch of times, and basically make the point that solar power, like all energy, is really just a form of integrated nuclear power. In the end, all energy comes from either nuclear fusion that powers the sun or nuclear decay that heats Earth's interior. And in this case, nuclear fusion is making the sun hot, and that energy is transmitted directly to Earth by photons. And those photons come directly to Earth, and we grab them and make solar power. And we'll be looking at some of these other pathways in future lectures. But solar is really the simplest. Photons come right from the sun, and we collect them on a solar panel. So I'll start with a question. Why, if you look at this map, it is a map of solar insolation at the top of the atmosphere. Yellow is a lot of insolation. White is less. In fact, almost half as much. So we're seeing that the highest latitudes in the Arctic get about half as much annual solar energy as the low latitudes. Why is that? Well, the main reason is because if you think about what it means to be at the high latitude, you don't have a direct line of sight at the sun. The sun is very far away, over here somewhere. And so relative to Earth, its rays are coming in at these equally spaced density everywhere towards Earth. Now, if you live at the equator, you are basically, the surface of Earth is oriented perpendicular to the direction at which these rays are coming in. And so in that case, at the equator, the full density of those rays strikes the Earth's surface. But if you live up at the North Pole, in fact, the angle between the land surface and the land surface and the incoming rays is more like 30 degrees. The land surface is very oblique to the rays, which means they're spread out almost twice as much as if you were at the equator. So the same density of rays coming in, but they're striking Earth at a much lower density. So that's really the first reason. Sun's rays intersect Earth's at a lower angle and are spread thinner. Also, if you think about what it means to enter the Earth at a lower angle, solar rays coming in at high latitude actually have to pass through a thicker level of atmosphere, right? If you imagine the atmosphere surrounding Earth, you have to go through more of it if you're coming in a little bit obliquely like that. So those are the two reasons that the high latitudes get less solar insolation annually. Now, the second point in the lecture is that latitude also affects the seasonality of solar production quite a bit. And understanding this starts with a review of the Earth-Sun orbital relationship. So recall that, of course, the Earth makes one rotation around the Sun per year. Okay, so it takes a year to go around. And of course, Earth is spinning on its axis, and one revolution around the axis is a day. Okay, so it'll spin 365 times as it makes its way around the Sun. Now, added on top of that is the fact that, of course, the Earth is spinning on a tilted axis. It's tilted something like 20 degrees away from vertical. Okay, so what that means is that in the northern hemisphere summer, the northern hemisphere is tilted towards the Sun. It's more directly facing the Sun. In the winter, it's facing away from the Sun. Okay, and then at what are called the equinoxes, or the halfway points between winter and summer, it's neither tilted towards nor away to the Sun. It's basically tilted kind of parallel to the Sun. So understanding this geometry is the key to thinking about why the seasonality of solar insolation depends on your latitude. And let's look at that. One big reason is that higher latitudes have bigger changes in the length of day between winter and summer. And the reason for that is plain. In this figure, in northern hemisphere summer, Earth is tilted towards the Sun. Now keep in mind, a day is a single rotation. So if this is rotating around the axis and it's tilted towards the Sun, and you live in Vermont right here, you're going to enter into the sunlit area earlier in the morning, and you're going to stay in that sunlit area till later at night. You're going to spend 15 hours in the sunlight. Okay? Now, if you were vertical at an equinox, you'd only spend 12 hours per day in the sunlight. And of course, in the winter, when the northern hemisphere is now tilted away from the Sun, you spin around in the morning into that sunlight, and the sun rises later, and you only stay in the sunlight for 9 hours of the day. Now contrast that with if you're at the equator. Doesn't matter. If you're tilted towards the Sun, you get 12 hours. Equinox, you get 12 hours. Tilted away, you get 12 hours. So the length of day doesn't change at the equator, and it changes quite severely up at the high latitudes. So the second reason that high latitudes have big seasonal differences actually has to do with solar angle. In addition to getting a longer day in the summer, the Sun actually tracks more directly overhead in the summer. So this is a bit of a tough geometry problem, but imagine that you're up at this latitude and the Earth is spinning, and as you spin into the light in the summer, the angle at which you're seeing the Sun is actually fairly steep. It's fairly directly overhead. Well, not quite, but it's higher. In contrast, if it's winter and you're tilted away, you come rotating around and you're looking across a longer tract of horizon. That Sun is going to appear lower in the sky as you rotate into it. And of course, it also stays lower in the sky. In the winter, the sun tracks very low across the sky because of that, because you're tilted away from it. And in the summer, when we're tilted towards it, it tracks almost directly overhead. So in summary, if you live at a higher latitude, you would make more solar energy in the summer, and you'd make a lot less solar energy in the winter, because you get longer days in the summer, and the sun passes more directly overhead in the summer. And this figure shows that it is the relative solar electrical generation off solar panels in Vermont by season. And we see that in July, we're making more than twice as much as we are in January and December. So it's a factor of 2 difference in electrical generation by season for solar energy. So I'll leave you with these concept questions. There's no quiz for this video, but tune into our next video where we'll look at how air pressure and weather also influence solar productivity.